this was supposed to be a very technical talk, but because not everyone works on the protocol level, so I'll try to simplify it, and if there's any like fundamental things that you understand, it's not that technical. But yeah, I think we have been thinking a lot about state, because that's a good reason why we do it, primarily to scale Ethereum. And state is one of the biggest bottlenecks that we have. So I will walk through like what are the problems that we have and what are some of our plans and ideas on tackling the problems. So just to give a recap on what Ethereum is doing on the scaling development side. So we are trying to scale Ethereum. So the upcoming fork will be in Amsterdam. So in Amsterdam, one of the focus that's related to scaling is one thing is what we call as block level access list. So block level access list is basically you put all of the state lists into the block. To do that, when you have this access list, how does it enable scaling is that it enables parallel execution. Not really parallel execution, but at least parallel reading of the state, so it helps to scale. And another focus for the upcoming Amsterdam fork is repricing. Because some of the opcodes, EVM opcodes, EVM operations some are very expensive, some are very cheap, so we are trying to balance it out. And one of the things one of the categories of opcodes that we are balancing is also on the storage side. If you're application developers, I would say that it's unfortunate because in the future you might see I don't have the numbers right now, but you will see an increase in state operations. So in real life, that would mean that if you send like a token or transfer some ERC 20 token, you get more expensive. But if you look at the aspect of it's not that bad, but in the future it might get worse. So, but this is how we want to balance out the opcodes pricing so that we can scale it, right? So one of the biggest focus is state. So and it's stopping us from achieving I guess. Yeah. Before I talk about future, let's talk about present. So, refresher or introduction. Ethereum state exchanges, account storage slots, and contract codes. So, to verify this state, we represent it in a cryptographic structure or data structure, what we call as authentication tribe, MET. So, imagine that you have top and bottom. Top is the account, and all of the leaves are all the for the top part, for the account tribe, all the leaves are all the accounts, and the bottom part where each account may or may not have its own storage tribe. So you have this two-tier structure. One of the bad things about this two-tier structure, MPT in general, is actually very inefficient for real-world pattern. If you look at the majority of the state, majority of contract nowadays, the pattern, the most common pattern is a mapping of address to some value. So for example, ERC20 mapping of address to balance. Some contracts have mapping of address to noise or die. Most ERC20 contracts also have a mapping of address to some value which is analysis. So if you put this like common pattern into MET, it's actually very inefficient because every key or every slot is hashed before inserting into the tribe. Hash means that it's random. When it's random, all of the keys, even though you know that, for example, if you call some function, you will access the balance and nodes. But in actual like low-level operations, you are actually doing random access, which is not efficient. So that's one of the problems that we have in MPT. Of course, there are many other problems. That's, for example, it's also not CT friendly. So yeah. So if you're interested in the state size, you can check out this page. But the current state size on the Ethereum, this is based on one of the execution times here, so it's about, I'm only measuring the try size here, it's 271 today, gigabytes. If you look at, it depends on the types as well. I think everyone has different numbers, but there are also some optimizations. For example, the actual state size you get is actually more than 270 because the leaf levels, all the accounts and storage slots are actually dedicated to allow for quick access. So yeah, but it's just as a reference for the state size if you're interested. So another thing that we also realize is that we don't understand enough about state on Ethereum. So I did an analysis on the state patterns just to find out like here are some quick statistics. So most of the accounts, 84% of the accounts are active for at most 1 year. I think that kind of makes sense because like how many accounts do you have? Think about how many accounts do you have and when's the last time that you transacted with those accounts. For me, I have an account for example 5 years ago and never touched it. Right? So yeah. So that's one. Then you have like 55% of the contracts are deployed once and never touched again, which is quite interesting because why are people doing this when you deploy a contract? If you think of it, one contract equals one application, I think that's kind of not true right now because people are doing different things with contracts. So I'm not sure why we have this method right now, but it could be spam, trying to scan this. Yeah. And then you have 73% of storage slots are written once and never touched again. This is very interesting to me because storage operations are quite expensive. And yeah, but people are writing to the storage, contract storage, and never really read it on chain. Definitely there are some, like portion of it are read off chain, which you cannot track. But yeah, so that's one thing. 97% of the contracts we use the same 9% of unique bytecodes, so we have 60 to 70 million contracts on Ethereum mainnet, but we only have like 1.7 million unique bytecodes, meaning unique, yeah, in this case you can call it unique application. So yeah, basically, for example, you have the same template, you have the same template, and most contracts will use it. So yeah, not all contracts are used, basically. Top 500 deployers deploy 57% of the contracts, so this could be an indication that relates to point to that these deployers could be doing something shady, I don't know. And last point is 88% of contracts have code size less than 1 kilobyte and 0.2% are more than 20 kilobyte. So there's one more thing that's also going to happen in Weihan as well, which is we want to increase the code size limit of Ethereum bytecode. So the current limit is 4 kilobyte. Tentatively, not confirmed, but we want to increase it to 32 kilobyte. So if you want to check out that analysis, you can check out the page. Right, cool. So future, right? How does what's on the Ethereum roadmap and what's on the particularly on the state side? So L1 scaling, we want to aim for 1 gigabytes per second, and the biggest consequence of doing this is state growth, because the more data that you write, the more data the node has to store, and this has a lot of problems. So this problem is what we call state growth or state growth. It's an increase in state size. So the first problem is state holding cost. Basically, for example, if you run a node, you have to have, for example, 1 terabyte or 2 terabyte of this storage. So that will increase. You might have to change it to some newer SSD, or you have to add like new storage. You have like 2 slots, you can make 2 slots in order to hold all this state. But I would say this is not the biggest problem because storage is actually very cheap. Theoretically, you can get a 10 terabyte of HDD and it's relatively cheap, but HDD is not fast enough, which relates to what I think is the biggest problem when it comes to state growth, which is the access cost. Every time the state size grows, for example, if the state size right now is like 10 gigabyte versus a state size of 1 terabyte, the same block, executing the same block will be much slower in the 1 terabyte state size. So this is the biggest problem that's stopping us from growing from like increasing the gas demand, because we are afraid that if the state size crosses a threshold, then nodes like irradiated nodes won't be able to execute the blocks in a given time slot, and it will cause like catastrophic failure in the network. So that's the problem that we have. And the third problem that is not so obvious but also very important, which is the increase in state syncing cost. To sync a photo right now on Ethereum is actually quite easy. I can sync a node using my whole network in 1 day. Depends on the clients as well, some even like few hours. But that's only because the state size on Ethereum right now is relatively small. If you're talking about a state size of, for example, 4 terabyte, I don't know if it's even possible to sync an entire state. So that's going to be a big problem. So if you see L1s or L2s, what they will do is that they snapshot to all the users. This is a snapshot of the full node at a certain block height. And yeah, that's usually the easiest way of tackling this syncing problem. But well, the downside is that it's not decentralized. Like, you have to trust that the full node, the snapshot is on the roadmap is stateless validation. Basically, it's the EVM. But you can imagine that in the future you can run your node on your smartphone or on your smartwatch. And the reason is because you don't have to execute blocks anymore, because you just have to verify the proofs in the blocks. So what will happen then is that full nodes or validated node simply drop the full state and shift to stateless nodes, right? Basically without any state. You don't have to store the state, and you don't have to have like a lot of storage. You don't have to re-execute a block, like the full block with the state, meaning the hardware requirement of running validated node is going to be much cheaper. So, and then that's cascades into more people are incentivized to run a node, it's easier to run a node, and then it helps with the decentralization of the Ethereum network. So that's the long-term roadmap that we have. But one problem with this roadmap is who holds the stake. Like, if for example, one day I have $1 million and I want to start a new infrastructure company, I want to compete with Europe, but I can't stake the state anymore. Like, I can't simply just run full nodes and get the state. Then how am I supposed to serve the state to my potential users? Right. So this is one of the very big problem that actually we have to solve. Because eventually that means that we are sort of like moving into a centralization world where the entities that will hold the state are basically block builders, maybe MBB searchers, RPC providers, and DeFi providers. So, which means that state syncing the state is going to be much harder. We kind of take syncing for granted right now, because you can just launch a node, and then you know that after some time you will be able to get a full state, you can verify the full state, and so on. So that's not going to be the case anymore in the future. So yeah, we are trying to solve it, and it also has some censorship risk, because so one of the things that we have in the future is FOSIL, basically a censorship resistant kind of a mechanism where the builders / validators have to force include a certain transaction so that they can all censor the transaction. But in order to build a transaction, a valid transaction, you need to have the state. Or at least to verify the transaction is valid, you also need to have the state. But if you don't have the state, then you can't do all of this. So some of the censorship mechanism might be useless in the future. Of course, there are some other limitations, but yeah, that's one of the risks. So solutions, there are a few targeting different problems. First category is state expiry. So the general idea is very simple. You have 80% of the state on the team right now is useless. We want to remove it, but we don't want to delete it. We still want to enable users to revive it if they want to. We don't want to delete it completely from the protocol. So that's state expiry. There are two variants, which I guess I can touch a little bit. So the first variant is what I call as not expired revive, where you have one portion of the state that's inactive, you just remove it. So in order for users to revive it, you just provide a local proof. So the good thing is that I mean there are many variants. The good thing is that it's relatively more straightforward. The proof size is the proof format is also more straightforward. But the downside is that depending on the variants, we have to trade off of effectiveness, proof size, and also user experience. So yeah, and then the second one is more radical. It's a major change where basically every 1 year, for example, you start a new, like you create a new database or you create a new tree, right? So this part is more effective, but because every time you start a new tree, it means that the number of state size is actually limited because you are bounded by time. So yeah, so that's quite effective in terms of like removing inactive state, but the downside is the proof for it is much more complex compared to the formal one. So yeah, that's the trade-off. Yeah.
The multi-error thing.
Yes.
Let's say you want to access state that was in a previous error. What happens? Because with the first one you say you revive it, right? But the second one, I'm assuming there's no revival. Then what happens?
Technically, you still have the level. So what happens in multi-error, at least with the field design that we have. So the original design is by the public, where you have multi-errors, you start a new error every 1 minute. You only hold the current error and the error previous error. So given one error equals 1 year, meaning that you only hold 2 years ago. So if you have to access something that's before that, what you need to do is to prove that, yeah, the proving problem is very complex. So for example, you have error 0, right now is error 10. You want to access something in error 5. So you have to prove that your state is in error 5, and you have to also prove that your state hasn't changed in the subsequent error. So like, if you look at the original idea, it's super complex. The proving logic is like, you have to prove a lot of different things in order to ensure that there's no double standing or you're not modifying the state.
Well, once you have finished that proof, then that old error state can be revived.
Yes, that's the gist of this category. Yeah. But again, yeah, I think regardless of this whole concept of state hasn't, yeah, I wouldn't say hasn't gained any traction, but it was started in like 2018, but people sort of gave up on it, and then we tried to revive it last year, at least since I've joined here. But the main problem is always on the user experience, because like imagine, right now, if you saw something on Ethereum, like you know that if you can always retrieve a key balance, but with this kind of mechanism, that might not be true anymore. I mean, you have a friction on like reviving it, so I think that's the biggest trade-off that we have when it comes to CSR. But yeah, the next part that we are exploring, which is before this. So if you're interested in like we have a CSR page, if you're interested in how much state we can save, this is the page that you can see. It also shows like the top 100 contracts in terms of state size on Ethereum. So yeah, that's just a playground for you to look at the data. So the next concept that is quite similar to state expiry but can be done out of protocol is what we call a state archive. Basically, we are storing everything in a single database. We want to split it into separate database, which is one for hot access and another one for cold access. Hot means active, cold means inactive. So the main goal is to decouple the state access from state load, because that's the biggest problem. Like state holding cost, the storage size isn't that big of a deal. So I mean theoretically this idea will also help with state holding cost, but you are still holding the state. So might not help too much. Think a bit long term, but the most important thing is that because most of the transactions will only touch the hot database, so balance, then it has to become persistent, but for like some of the state that relates to contract logic itself, they could be stored in temporary storage. Right now, the way that is, there are a few ways that we can store things on Ethereum. You have memory, but that's memory that's based on per core frame, per function. Then you have transient memory, that's per transaction. Then you have persistent memory, that's forever. Persistent storage, that's forever. Then you have blobs. So blobs are ephemeral, they be stored for 21 days or 30 days, etc. But that's not accessible from the EVM. So temporary storage, maybe our temporary storage is like blobs for EVM. So that's one of the ideas that we are exploring. We have, we have the EIP, A1 move like, but we are still trying to get the feedback from the developers and see if this is something that they can use. Yeah. So the main incentive of using such feature is that storing and temporary storage will be much cheaper compared to the persistent storage. Yeah. And then the third idea is something that I personally have been thinking about a lot, which is address-based storage. Like I mentioned just now, most of the patterns, most of the state are address-based, mapping of address to some value. And the current state layout isn't optimized for it. So how we optimize the state layout to do something like this? And it's going to help for not just on the database efficiency level, but also on other things like experiment will be one of it. But in the future also partial state instance, which I'll touch on later. And the next thing that I think inevitably we have to do for your clients, I believe, my personal belief is that we have to move from key value small database to something that's more custom built. So I was actually checking out Weihan because the co-founder just released a very long, detailed article on how they built the Weihan. So Weihan is what Weihan did to make database operations more efficient because it's a custom built database. So if you're interested, you can check out this latest article. But we also have other stuff. So we have TriDB from Coinbase. We have Salt from Weihan. This Salt is not MPT compatible, but it actually uses some of the ideas from local tree, if you know what's the local tree. And then we have randomized Africa Mini. But last time I heard it wasn't maintained anymore. But yeah, that was still one of the initiative. You have Sovereign Labs and OMT near optimal local tree, which is binary tree based. And then we have Layer Zero's QMD, local database. So these are a few custom built databases for local trees in general. Yeah. Right. Then the next big topic that we have on Ethereum software is to do a tree change. So we want to shift from MPT to something that's better. So the current proposal we have is to shift to binary tree. Previously it was local, but now it's binary. So doing this shift allows for a few good things to happen. The first one is it's going to be prover friendly because MPT is not prover friendly because of the things that I mentioned. So one is cache, another one is IRB. IRB is very complex. I think not an expert in this matter, but I think those are the two things that I can think of. The second thing is also we want to use post-quantum secure hash function. So we haven't decided on what hash function are we using yet. Could be Poseidon or I guess Picture. Yeah, this is the option. These are the options that we have. And the third part is on the locality, basically the problem that I mentioned for MPT. By grouping storage more efficiently, you can actually make the layout more efficient, which means for users, it will be lowering gas costs. For high-end execution time, that would mean that the database actually be smaller, depending on how you design how you write the database architecture. So yeah, that's one of the big things that we have on the roadmap. And the last part is on partial statelessness. I think this is a relatively new concept. Basically, we want people to be able to hold the state that they care about. So basically, like if you are, for example, if you run a full node, care about some of the accounts and some of the contracts that we interact with. So why not just store them and that's it, right? So we want people to be able to run node easily and be able to hold their own state so that they can so that they don't have to rely on RPC providers in order to submit the transaction. So that's one of the things that we were trying to build and also trying to motivate people to use it as well. So previously we thought that we have to shift to KPM or we have to shift to local or binary in order to do this. But actually that's not the case. With the current technology or with the current tools that we have, so we have something called light client and snap sync. So snap sync is a syncing mechanism for 3 of the clients that we have now. So we can combining these two technology, we can actually do partial status. Right? We can actually run a partial status node already. And with the upcoming platform, block level accesses, files, that would make it even easier. So yeah, we're trying to build a prototype and hopefully people can use it. And the second, not really a new idea, but what I want to do in regards to holding lower states, so work on VOPS, which is validity only partial statelessness. Because again, if you think about a level architecture where most of the nodes are stateless, then the public mempool will essentially be dead. Why is it dead? Because to verify a transaction is valid or not in the mempool, the public mempool, you have to have the state. So VOPS is an idea where we hold the minimum amount of state to be able to verify the transactions so that the public mempool is not dead. So that's one of the directions that we have as well. So yeah, I think that's it. The future of digital state is bright. At least that's how I see it. So yeah, if you're coming to UCC in less than 2 months, I'd like to invite you to Failure Summit. We're organizing something where we talk about different things related to the state. So yeah, check it out. That's all. Thank you. Questions? Yeah.
So basically, I have questions. You mentioned that some of the states are, the old states are archived here. And definitely we have to have resources to acquire all the old states. So what actually is the incentive that actually drive those old nodes to store those archive states so people can retrieve when this is needed?
Are you talking about the protocol level or like application level, RPC level?
I'm talking on the protocol level itself.
So, wait, sorry, can you repeat your question?
So it's like some of the states right there are used, they are archived. Let's say that past transactions and old transactions.
Yeah.
So definitely one time that people might need it in the future. So what actually drive all those actually to store those old data so that it can be retrieved for later use.
Are you
Basically the incentive.
Or the incentive to store all data in your archives? So the incentive is that, I think it's not incentive, but well, the easiest thing that we can do is to delete it. But why we don't want to delete it and move it to archive is because we can't delete it. Because you can imagine that right now, I have 1,000 ETH, for example. Well, one day I want to make the comma, 10 years later I wake up, my ETH should still be there. So it's not a trade-off, but it's something that we wouldn't want to do at all. Like, that's why we want to move it to. So the thing is that everything that regards to state, it has to remain inside. It shouldn't be removed at all. The only thing that we can do is to, like what I mentioned, separating it into different storage and making it more expensive to retrieve it but never delete it. So, yeah.
But the storage is like still maintaining a decentralized settings, right?
Yes.
I'm not sure what the opcode I think has been renamed, but there used to be one called the suicide one where you kill the contract.
Yes.
Yeah, it's self-destruct, yeah. And so that, is it still negative gas? Like you get a refund?
No, I mean, previously, I guess historical context is that people are using the suicide/self-destruct opcode to do something like a gas token thing, where because you get the refund, that's why I forgot how the refund that you get is actually more than the transaction,
Yeah.
the cost of the transaction, but that's no longer the case. I think it's already solved. I think
Yeah, I mean, I wasn't really going there with that. I mean, just saying that that was like a very early version
Yes.
of an economic incentive for you to sort of clean up
yes,
state you no longer need,
yeah.
right? So, are there any other like economic mechanisms rather than, I guess, you could say data structure-based mechanisms which are being considered to reduce the state?
Yeah, I think the main problem with imposing like new economic model on the state is that the previous state, the previous contract, like all the contracts that they brought before, they don't like account for all this new economic model. That's why I think the whole idea is called like one of the directions is called state rent. But I personally don't think state rent is a solution for Ethereum specifically, because if you want to do state rent, you should do it from the start, because people can design for it. But I heard that I didn't look into it fully, but I heard that okay, Solana has this model, but it hasn't been working for them for state rent. I don't know why, but personally I didn't look into like the renting model, but rather we just have to accept the fact that we did a bad design decisions when it comes to the state. So all the previous state has been taught before, they will stay in protocol forever, which is